Up next is what is known as the composition of functions. You can compose functions like f of g, f of f, g of f, and so on. But before we go any further, let's make sure we understand the difference between notations. If we look at f dot g, what we are looking at is the multiplication of f and g. If I write f followed by a little hollow circle of g, this is the composition that we're going to study. Let's start with f of g. That's where you take the g function, the expression of g, and we plug it into f. Now, you can also do f of x, which is where f literally gets plugged into itself. G of f of x is not the same as f of g of x, because here you're plugging f into g. In fact, we'll use this as our very first example. How are you going to evaluate g of f of x? Well, let's start with using a very specific value, in this case 3. The idea is that 3 needs to be put into the f of x function first. So I'm going to represent this with a function box in which I stick 3 into the function box. Since we know that 2 minus 3 times 3 happens to equal negative 7, my output will be negative 7. So f of 3 is negative 7. This is the value that immediately gets plugged into g. I take that value, negative 7, and I put it into the g function box. Well, now negative 7 is going to be squared, and it's then going to be added to 5 times negative 7, and this is going to produce a result of 14. So what I can say is g of f of 3 eventually equals 14. One of the first things to remember about compositions is that f of g of x does not always equal g of f of x. I'm not saying they never equal, but I'm actually saying more times than not they don't equal. Let me demonstrate that by actually computing f of g of 3. One of the things I tell students when learning compositions is the 3 that's touching the g is sort of the way to remember how to begin. You need to plug the 3 into g immediately. And so 3 squared plus 5 times 3 works out to be 24. That 24 then gets put into the f function, and 2 minus 3 times 24 works out to be negative 70. So f of g of 3 equals negative 70, g of f of 3 equals 14. Right there alone, that shows that f of g of x cannot equal g of f of x. Compositions of functions can be found using tables and graphs as well. The first example will be m of n of 2. Let's use this little visual trick to remind ourselves that we need to compute n of 2 first. So we go to our table, there's 2 for the x, we'll go all the way over to n, and we'll figure out that we need to be at 0. So n of 2 may be 0, but that's the value that we now have to actually plug into m. So we go back to our x's, we find 0 now, we go down to where m is, and we realize that that value is 6. So our result, m of n of 2, equals 6. If we move on to p of m of 2, we're going to need to find m of 2 first. So back to 2 we go, but this time we'll only go down to the m column, which is 4. And that's how we get p of 4, which immediately gets plugged in. But p of 4 requires us to go to the graph. So here's where the value of 4 is. We'll find the graph point. That point happens to be 4 comma negative 6. And if 4 is what goes in, then negative 6 is what comes out, and negative 6 is our result. So p of m of 2 works out to be negative 6. Let's do one more example of this type in which we compute n of p of 2. We'll use our little visual trick to remind ourselves we need to compute p of 2 first. Since p is represented by a graph, we'll go to where x equals 2, we'll find the height, which happens to be at 2 comma negative 2, so our height is negative 2, and so p of 2 works out to be negative 2. And that's the number we need to plug into n. But n is represented by a table, and so we'll need to go down our x's to find where, well, x equals negative 2. Not a match, not a match, not a match, not a match. In fact, I don't see negative 2 anywhere on this table. And this is going to cause a problem because n of negative 2 is undefined, which means n of p of 2 is undefined. This leads to an important rule that is often overlooked. You have to understand the domain of g of f will consist of only the x values in the domain of f for which the range of f of x is in the domain of g. Huh? All right, let's put it in terms like this. Our g that I'm talking about is really going to be known as n. The f that I'm referring to is really being represented by the p. So, first off, we have to look at the domain of f, or in this case, the domain of p, and that's all reals. So, we would start with all possible reals could work overall. But what ranges of f of x are actually going to work up here? Well, let's take a look. I have -1 as an option. The only way to get -1 out looks like it's right there at 1.5, comma, -1. Therefore, only 1.5 is a number I can actually plug in to get -1 out. Well, I also have 0 as a height. 0 height occurs when I plug 1 in and I get 0 out. So 1 is an option. Here I have 2 coming out. That's only if I plug in 0. And finally, I have 6 as being a possible height right there, but only if I plug in -2. So, I guess what I'm saying is my domain can only work if I plug in -2, 0, 1, or 1.5. I may have all reals for p, but only these 4 numbers will produce the results that I can use up here. And that's what I'm saying. So, from an analogy standpoint, you almost want to think of putting a filter on here and saying, okay, sure, all numbers can go in here, but we have to catch the numbers that are going to cause issues down here. And the only numbers that we can pass through safely are -2, 0, 1, 1.5. And that's pretty much what this whole business down here is all about. Limit your domain to numbers that work both for f, which is in this case p, or g, the numbers that come out will also work for n.